In this video, we are going to cover the Cauchy integral theorem for closed paths and also discuss path deformation. So this is our overview slide, which we'll spend less than 5 minutes on before we go through these topics in more detail and more examples. First, because the Cauchy integral theorem involves analytic functions, we're going to review the Cauchy-Riemann conditions for analytic functions. So the sufficient conditions for a function to be analytic is the partial derivatives of u of x and v of x exist, are continuous, and obey the Cauchy-Riemann conditions which are listed here. We are going to use these Cauchy-Riemann conditions when we do a proof of our Cauchy integral theorem, but before I go to that, I will say the Cauchy-Riemann conditions are really useful, and we see that in this proof of this theorem. However, there are many examples where we don't formally show that a function is analytic, but we work with that. And one of the things I want to, and I'll give you examples of that, but I also want to just flat out tell you that polynomials are analytic, exponential functions are analytic, sine and cosine is also analytic. So you don't need to show me all of this when you have polynomials, exponents, sines, and cosines. But as I said, the Cauchy-Riemann conditions, you need to know them so that we can prove this amazing theorem, the Cauchy integral theorem. And this is one that you should be very thankful for. It says that if we have a function, it's a complex function, and it's analytic in some region of the complex plane, if we consider an integral along a closed contour, so this is important, it does need to be a closed contour, which lies entirely within the analytic region, then the integral is equal to 0. And here we have the picture. So we have a closed curve. So if a function w of z is analytic on this curve and also in the interior of the curve, then the integral over the curve, the line integral of that function over the curve, will be equal to 0. So this theorem could potentially save you a lot of work. But the other thing this theorem does for you is we get these contour deformation. So a result of the Cauchy integral theorem is that the contour of a complex integral can be arbitrarily deformed to an analytic or inside an analytic region without changing the value of the integral. So for example, if we're integrating from a to b on this line integral, let's call that line or curve c naught. We take the integral of some function w of z, c naught. Let's also say that w is analytic in this region. Then we can draw this other curve, and it's a closed curve which is dotted in blue, and I'll call that curve c. So it's a closed curve, it's blue, it's analytic in the region, so that means the integral over this curve is 0. So let's just add that to this one here. Why don't we? So here's our integral over c naught, and we're going to add our integral over the closed curve c of wz. And remember, this is 0. So what that tells us, if you look at this, let's just look just at this portion where the black, the c naught, intersects the blue, the c. For the black region, from here to here, the direction of the integral is going upwards. But for c, from here to here, the direction of the integral is going downwards. It's the same line, just the direction is reversed, which means these two integrals are negatives of each other. So when you add the integral just from this piece to this piece where they intersect, the blue and the black will cancel each other out, which means that this integral now, we can just kind of cancel out this middle part where they intersect, and our original integral over c, over here, c naught, is equal to the integral over this new curve, c naught prime. And we will use this in future videos in order to avoid different points. So we can integrate, and we can, like, if there's a point here we don't want to integrate over, we can just go around it, and we still have the same integral. So that's it for our overview. So now we can go over everything in more detail and with more examples, especially over here in the Cauchy integral theorem. First, let's just quickly review the Cauchy-Riemann conditions for analytic functions and also the sufficient conditions to be analytic. So first we have this formula here, our Cauchy-Riemann conditions. So for example, if we wanted to determine if the function wz equals z squared, which is x plus y plus iy times x plus iy, which is x squared plus I 2xy minus y squared, is analytic. First, we need to write this in the form of a u of xy, because that's what, and a v of xy, where u of xy is a real function and v of xy is a real function multiplied by I. So we group our real portions together and we group our imaginary portions together. Now we have u of xy here and v of xy is 2xy. So then we can take the partial derivative to check out these Cauchy-Riemann conditions. Partial derivative of u with respect to x needs to equal to partial of v with respect to y. So here we have partial of u with respect to x, partial of v with respect to y, and we see they are equal. And then we check partial of u with y is equal to negative partial of v with x. So this is partial of u with y, and it's equal to negative partial v with x. So this function satisfies the Cauchy-Riemann conditions, and then to check that it's analytic, we need to verify the partial derivatives u of xy and v of xy exist, and they do because we've calculated all four. They are also all continuous because they're all lines, right? 2x, 2x, those are lines. Minus 2y, 2y, that's a line. So they're all continuous, and finally they obey the Cauchy-Riemann conditions. So there is another point I'm going to make for this video. It's like this is a nice illustration of the Cauchy-Riemann conditions, which are important. They're going to play a part in the proof of our next theorem. But often when you do problems, just like in first year calculus, at some point you don't verify that the derivative from the left approaches the same value when you approach from the right. You just kind of know, or you can look at, or you can graph and determine if something is analytic. So one thing I'm going to say for me, for my classes, I would say examples of analytic functions includes polynomials, exponents, sine, cosine. You don't actually need to do the Cauchy-Riemann things here to prove it. To me, you could just say it's a polynomial and it's analytic. And then also, many functions, just like in calculus, you can tell when they're not analytic. And I'll give you some examples of that as well, including the next example. So here is our next example, and we worked this in our last video, so I'm not going to go through it in detail, but we looked at wz equals 1 over z, and then I wrote that as 1 over x plus iy, and then I multiplied by x minus iy, the complex conjugate, on the numerator and denominator, so that I could get rid of the I in the denominator. And then we separated that out to a u of xy and a v of xy, and we saw that the Cauchy-Riemann conditions were satisfied. And then we looked at the partial derivatives. They're defined, but they're actually not defined everywhere. They're not defined at 0, 0. So for that reason, right, they don't exist everywhere. They don't exist at 0, 0. For that reason, this function is not analytic. But honestly, you can look at this. This is 1 over z, just like 1 over x. You know there's going to be a problem at z equals 0. I will say this last example, which we did in our last video, which is w is equal to z times the complex conjugate. So here I have z, its complex conjugate is equal to x squared plus y squared. So this surprisingly does not satisfy the Cauchy-Riemann conditions except at z equals 0, 0. So this function w is not analytic everywhere because a single point cannot be analytic because it needs a neighborhood around it, and that's what we had discussed in our last video. So this is kind of surprising. So this is one where you multiply, and it's worth remembering, where you multiply by the complex conjugate. It is not analytic. Now continuing with our next topic, the Cauchy integral theorem. Let wz be a complex function which is analytic in some region of the complex plane. Consider an integral along a closed contour which lies entirely within the analytic region, then the integral is equal to 0. So quite a powerful theorem, and we're going to use the Cauchy-Riemann conditions to give that proof. Before I do examples of this theorem here, I'm going to derive or show you why the integral is equal to 0. I think this derivation is important because it uses the Cauchy-Riemann conditions. So I think it's worth looking over. Otherwise, I would have put it at the end of my video. Anyway, so let's say we have a function w. This is a complex function of z. And by the way, I guess your book underlines these complex numbers, and that's never been a habit of mine. So I'm just not even going to try. So these are complex numbers, generally w and z our complex numbers. The other thing I'm going to tell you, if you take a whole entire complex analysis course, after a while you get in the habit of putting a z across a line here on your z, because otherwise they start to look like the number 2. So this is kind of a good habit when you're working in complex analysis. Anyway, so wz is some function of z, and we're going to write that as a real portion and an imaginary portion. And again, I'm going to write dz equals dx plus I dy. So then when I take my integral of dz w of z, I can then separate out, first my dz becomes dx plus I dy, and my wz, I'm going to separate out my real portion and my imaginary portion. Now when I multiply out, I get dx u of xy, and then I'm going to do this multiplication, I dy times I v of xy. So the i's give me a negative, and I have my dy v xy. Now I also need to multiply my I dy times my u of x, so I factor out my I, and I get dx here to here. I'm sorry, that's this term. I factor out my I, and I get dy u of xy, and then when I multiply dx times I of vy, I get my dx, and again my i's factor out v of xy. This is going to allow me to break this up into two integrals. This is my first integral, where I take this first part here, which does not involve I, and then my second integral when I factor out the I. Remember, I is just a constant, so I can factor it out, and then my integral of this part here that is multiplied by I. The next thing I'm going to do is introduce Stokes' theorem, which I have rewritten here. And just to remind you, Stokes' theorem relates a line integral over a vector over some curve to the curl of the surface integral, that is the curl of that vector field, integrated over the surface that's created by your boundary, your line, and your curve. So when we use this, we're going to realize that our vector field, our v, we're going to use our w because it does define an x-coordinate and a y-coordinate, and technically you can say it defines a z-coordinate, it's just equal to 0. So here, for the first part, this first integral here, our u of xy is our first coordinate, and our second coordinate is minus v of xy, and then of course z is equal to 0. So now we can take the curl. So the curl is the I, j, k direction, partial with respect to x, partial with respect to y, partial with respect to z, and then we have our u of xy, our first coordinate, our second coordinate is minus v of xy, and our z coordinate is 0. So now we take the determinant. So when we take the determinant in the I direction, we let me circle this. Looking at the I direction, and we cross out the row and column of the I, we get partial with respect to y times 0, so that's 0. Partial with respect to z of v of xy, well, v does not depend on z, so that's 0. So we have 0 in the I direction. Similarly, in the j direction, we're going to have 0 minus, and u doesn't depend on z, so it's 0, so 0 in the j direction. And finally, in the k direction, partial derivative of v with respect to x, and there's a negative, minus partial derivative of u with respect to y. So this is what we have in the k direction. This is our cross product. Similarly, I can take this integral here, and so, I dropped the I. Okay, let me put an I here. So I have our I, and then integral over c dx v of xy plus dy u of xy. I can apply Stokes' theorem. I can take the curl, apply Stokes' theorem, and this is what I'll get. The surface integral dx dy, partial derivative of u with respect to x, minus partial derivative of v with respect to y. And the next thing I'm going to do is use the Cauchy-Riemann conditions for analytic functions, where we see that du dx is equal to dv dy, which means this part here goes to 0. And we also have am I doing this right? Yeah, du dy is equal to negative dv dx, which means this part over here goes to 0. So let me just put arrows. That this here imply, or I guess I should do the arrow the other way. This here implies that this goes to 0, and this over here implies that this goes to 0, which means our original integral, which is the sum of these two integrals here, is equal to 0. And that's equal to 0. Again, we need to make sure we understand that W is analytic along the closed curve and inside the entire curve. As far as proofs go, that wasn't too bad. So now we're ready to do some examples. This next example is to evaluate the integral over c, z squared, where c is the curve represented by, or given by, the absolute value of z is equal to 1. Usually the first thing I do is show you what c looks like, but I also want to point out something about this function, z squared. And this is our previous example where we worked out w equals z squared. We put it in terms of u of xy, v of xy. We did the partials. We found that the Cauchy-Riemann conditions and the other conditions, sufficient conditions to be analytic, were all met. And so it is an analytic function. But I'm going to add that for my class, because this is a polynomial, I'm okay with you telling me straight away that this is an analytic function without having to see all the Cauchy-Riemann conditions. Because this is on the internet, if you have a different teacher, they may want to see these, that you've satisfied the Cauchy-Riemann conditions and these other conditions for the partial derivatives. So that's something you should be clear about with your teacher. So if you're in my class, for a polynomial, I don't mind if you just skip showing all of this and just say, oh, this is analytic. So we know it's analytic everywhere. Also, I do generally start off by drawing my curve C, and Z is less than 1. Well, that's the curve of radius 1. So I've drawn it here. It's analytic everywhere, so it's certainly analytic on the curve C and its interior, which means that this integral here, the integral over c of z squared will be equal to 0 according to the Cauchy integral theorem. Our next example is the integral over c, and I have c, it's the same z, c, where absolute value of z is equal to 1. In other words, the circle of radius 1, and the function is 1 over z. This also was our previous example. We had done all the work of taking all the partial derivatives to show the Cauchy-Riemann conditions were met, but then we found that, well, the partial derivatives also have to exist, but actually they are not defined at 0, 0. So they are defined everywhere except 0, 0, and the Cauchy-Riemann is satisfied everywhere. So our conclusion, when we did this previously, we said W is analytic everywhere except at z equals 0, 0. In this case, for this curve, you can see that the point 0, 0 is interior to the curve. So it wouldn't have bothered me not to see all this work here, because the critical thing here is that at z equals 0, our function is undefined, our partial derivatives are undefined, and therefore we can't use the Cauchy integral theorem. And in fact, at this point, we don't have a way of evaluating that integral. And I just wrote that out here. Since W of z is not analytic at z equals 0, 0, which is in the interior of our curve, we cannot use the Cauchy integral theorem. And at this point, we don't have a way of evaluating the integral, but we will in a future video. I have one more example now. The integral over c, the same unit circle, and our function is z squared over z minus 2. And it looks sort of similar. We have this polynomial on top. We have something here that could be equal to 0 sometimes, like when z is equal to 2, but otherwise it's defined everywhere. As I had mentioned, normally I like to draw my curve first. So here's my circle of radius 1, and as I mentioned, at z equals 2, wz, our function here, is not analytic. So I'm just going to go ahead, and this should be a z, not an x. I'm going to go ahead and note that. So here I have my function, w of z is equal to z squared over z minus 2, and it is not analytic at z equals 2, but wz is analytic on our unit circle, on the curve, and in the interior of our unit circle. So we can apply the Cauchy integral theorem, right? Because this point that's not analytic, it's outside our circle, which means that our integral over c of z squared over z minus 2 is equal to 0. So those are our examples for the Cauchy integral theorem. So I would hope that I got an exam question on this because it's so easy. But anyway, the next topic is contour deformation, which is fascinating. One, like how often do you talk about deformed things in mathematics? And two, it's kind of like it really gets used. It's almost like it's abused, but it's very clever. It gets used all over the place. So I have those drawings, the 3 drawings here, made a little bit bigger so we can look at that. So let's consider this integral. Let's say we want to integrate over this line, our path, which we're going to call C0. And it's a path from the point A to point B. So here we have the integral over C0 of our function wz. What we can do then, by abusing this Cauchy integral theorem, is we can add this other closed curve integral where part of it intersects part of our path C0. So over here, between this point here and this point, you can see our blue closed curve path C intersects with our black line drawing C0. Now, as long as our closed curve C is somewhere in the area where our function w of z is analytic, any integral over this closed curve C is going to equal to 0. So let's just assume that this area is an area where wz is analytic, so I can just add this closed curve integral, the integral over the closed curve C of wz, because it's going to equal to 0 because it's analytic. Now let us turn our attention where these two curves intersect, where C0 intersects C. They're the exact same curve, so when we, except that they're in opposite directions. So when we integrate over from here to here, our C0, and we integrate from here to here, our C, they're going to have the same value except for a negative sign. In other words, the integral just in this path here of w over this black line is going to be the negative of the integral of w over the blue line, which means when we add them together, those pieces together, they're going to cancel out, which means kind of like this whole part of the path doesn't contribute anything to this integral here. So in other words, we have this integral now when we take out the paths that intersect, and we have the fact that this integral now, the straight line integral, is equal to this integral here, where we just kind of bypass a little area between right over here. So this will become convenient if we have some inconvenient point, maybe where things aren't defined, we can just kind of bypass them. So we'll be using that later in future videos. And that, again, is our theorem of contour deformation, and it's like a total abuse of the Cauchy integral theorem, but it's an amazing kind of very clever way of abusing this theorem. To review what we have covered in this video, we first reviewed the Cauchy-Riemann conditions for analytic functions. That is, if we write our function in terms of u, a real function plus I times another real function, then we want du dx, the partial of u with respect to x, to equal to the partial of v with respect to y, and we want partial of u with respect to y to be equal to the negative partial of v with respect to x. The other conditions to be analytic, to guarantee a function is analytic in some portion of the complex plane, is the partial derivatives of u of xy and v of xy must exist, they must be continuous, and they must obey the Cauchy-Riemann conditions. And then I also mentioned that we can, you can use the fact that polynomials, exponents, sines, and cosines are analytic without going through the formal demonstration of this. This Cauchy-Riemann condition for analytic functions is very useful, though, and it is useful sometimes because you have other more complicated functions that it may not be clear whether or not they are analytic, but also it comes in very useful for proving the Cauchy integral theorem, which is kind of an amazing theorem and one that you would hope ends up on one of your exams. So let W of z be a complex function which is analytic in some region of the complex plane. Consider an integral along a closed contour C which lies entirely within the analytic region. Then the integral is equal to 0. And here's the picture. We have our closed contour C. So if our function that we want to integrate is analytic along the contour C as well as interior, then that means the integral of WZ along the contour will be equal to 0. Last, with the Cauchy integral, we use this theorem in order to do contour deformation. So we deform our contours that we're integrating over. So a result of the Cauchy integral theorem is that the contour of a complex integral can be arbitrarily deformed. So that's what's amazing, to an analytic region without changing the value of the integral. So here we looked at if we want to integrate along this straight line, which we'll call C naught, going in the direction from A to B. We can add, as long as WZ is analytic in this region, we can add this little closed contour, the blue C. And if W is analytic in this region, then adding this closed contour, the integral over this closed contour, is going to be equal to 0. So we can just add it. And you know, I drew a nice contour that was sort of like a semicircle, but it could be any funky closed contour. So yeah, that's what it means, arbitrarily deformed. Anyway, so you can add this extra contour and it really adds 0, but technically it's there and it's drawn such that it does overlap some portion of our original contour, but it goes in the opposite direction. So that means for this portion where they overlap, the integrals will cancel each other out because they're equal to negatives of each other. And then what you're left with is this contour here. It's the contour without the overlapping portion. So our original contour will equal to this new contour. And as I said, this can be arbitrarily deformed because our C, and I'm going to draw this in yellow, could have been a closed curve. Again, the important thing is we overlap, but then it could have this crazy stuff as long as it's, you know, analytic in this region, you can arbitrarily deform it into something crazy. We will see this contour deformation in future videos. It is quite useful. But for now, that's it for this video. Thank you for watching.